Welcome to our replacement lecture for the snow day on March 15th. Here we'll talk about the MAC-1 in a little bit more detail. Hopefully by now you've had a chance to read over the Canvas documentation, but we're going to summarize a few things here and walk through an example of how this machine will execute. So what is the MAC-1? Well, in general, it's a simple assembly language interpreter which simulates a bare bones computing device. In this lecture, we're going to focus on the machine part, not really the assembly language part, although we'll get an example of that, as this is a precursor to everything else. Remember that your project will focus on the GUI interface, the machine design, and, time permitting, the execution engine. The MAC-1 is what we call a macro architecture, and it simulates what's called a level 2 machine. Now, using this diagram, the level 2 machine is the machine instruction level. In general, what we're going to be doing is executing a program or a series of programs based on what the user gives us. In a sense, we're going to be implementing the underlying components of a simple machine and its execution engine. The MAC-1 is a simple stored program computer. Now, if you had IST 110 with me, or maybe even CompSci 101, you will have seen a diagram similar to this one, although a bit bigger, which was called von Neumann architecture. In general, that's what we're simulating here. We're simulating the notion of a CPU and a main memory, which communicates via some bus mechanism. Our main memory will have 4096 words of memory. Word is an architecture term which has differing meanings depending on the machine, but for us, each word will be 16 bits or 2 bytes. The equivalent Java data type for this size of word is short. We will also have 5 registers available. Remember that registers are nothing more than memory elements that are housed on the CPU. They're housed there so that the other components of the CPU, the ALU and the PCU, can have sort of a scratch pad with which to work. Accessing the registers is a lot faster and a lot more efficient than accessing data from main memory. And often registers hold the most recently used data, as well as some summary information that the CPU needs to execute. There are also 3 addressing modes in the MAC-1, but we'll get to that later. Here are the 5 registers. Of these 5, the first 2 are the ones we're going to use the most. The accumulator, or the AC register, is used for math computations. It's also used indirectly to move data to different memory locations and other things. The program counter, or the PC register, stores the memory address of the instruction currently in use. Remember that a stored program computer means that when you run a program, its instructions are loaded into main memory, and then the CPU executes those instructions one instruction at a time. The other 3 registers, the input status register and the output status register, as well as the stack pointer, will be used less frequently. ISR and OSR are all about input and output, and the stack pointer is useful when we need to move from one location within our instructions to another. In terms of input and output, we're used to doing things with items like cout or cin or system.out.println. Here it's going to be very limited and very basic. The type of data that users can enter is going to be very limited, specifically simple integers in the range 0 to 127. Input and output will be a matter of reading from a particular memory address and writing to a particular memory address. By doing this, we're going to be simulating input and output. So how do programs get loaded? Well, it's really a 2-step process. One of these steps we will be working on, and one will be done for us. The first step is to take a file of assembly language instructions and load them into an assembler. The assembler produces an intermediate file in the form of an XML file. This XML file is then loaded into the main memory via a loader program. It's this loader program which we'll be working on in a few weeks. Once the instructions are in main memory, they're ready to execute. So how do programs get run? Well, they get run a lot like your programs that you may have done in C++ or Java get run, using something called the fetch, decode, and execute cycle. We fetch an instruction, we decode it, and we execute it. An offshoot of that is that data may be output. Now, output here doesn't necessarily mean to the screen. It can mean that data is placed into a location in main memory. It can mean that data is placed into a register. It can also mean that a status flag inside the CPU is set. The PC register keeps track of the next instruction to be executed, and we use other registers as we need them, and a stop instruction will end the program. Otherwise, this cycle will continue indefinitely. Let's take a look at a simple assembly language program to demonstrate how the MAC-1 simulated machine would work. On the left, you see a series of assembly language instructions. It's important to note that the numbers shown here are in hexadecimal, or base 16. In the middle, you see the two registers we're going to be dealing with these instructions, the accumulator and the program counter. They are both shown with values in base 10. On the right, you see the partial contents of main memory, and again, both the addresses and the value are shown in base 10 for simplicity. The first instruction, indicated by the arrow, will be the load direct instruction. What this is asking you to do is to load a value from main memory address 16 in hexadecimal into the accumulator. Well, 16 in hexadecimal is 22 in base 10, so if you look at memory address 22, it has the value 21. Ultimately, once we execute that instruction, that's the value that gets loaded into the accumulator. Please note also that the program counter moves from 0 to 1 to indicate that memory address 1 will contain the next instruction. This next instruction is add direct, which means we want to add a value from main memory to the accumulator value. In this case, it's the value at memory address 17, which is 23 in base 10. If we look at main memory address 23, we see the value 23. This value will be added to the accumulator. So 21 plus 23 will give us 44. The program counter also goes up by 1. Store direct is our next instruction, meaning we take the value in the accumulator and store it directly into main memory at memory location 18 in hexadecimal. Now 18 in hexadecimal is 24 in base 10. So we're going to put the value 44 from the accumulator into memory address 24. Once that's done, the program counter increases by 1, and we again have a load direct instruction. What this is saying to do is to load the value from memory location 17, which is 23 in base 10, into the accumulator. We do that, and it overwrites the 44 that was there, and the program counter increases by 1. The next instruction is subtract direct. Now this is saying to take the value at memory location 16, or 22 in base 10, and subtract it from the present value in the accumulator. So it will involve the accumulator value 23 minus the value at memory location 22. So it will be 23 minus 21, and 2 will take on, or will become, the new value of the accumulator. PC also goes up by 1 as normal. The last instruction before the stop is store direct. This is saying to take the value in the accumulator and store it directly at memory location 19, or 25 in base 10. So the value 2 will be placed into memory address 25. At this point, we've hit the stop instruction. This will end the program. Next time we'll walk through another example in class, so stay warm, continue working on the 2 items for this week, and I will see you on Friday.